The language is a powerful tool that allows human beings to communicate using symbols, sounds, and others. And in the last years, natural language processing and speech recognition has been the subject of development in artificial intelligence, human-robot interaction, and collaborative robotics. Into this last field, the collaborative robotics, we aim to create an autonomous and smart system for execute a disassembly task. That is why we don't want to control each action of the robot, because even when it sounds great for representation, for example, commands the robot using the voice all the time could be tedious and not practical in the industry. Then we use some of the previously presented technologies focuses on the interaction between the human and the robot for solve problems that could appear in the process. Let's start understanding our experimental prototype. Our prototype is built on ROS, which is a robot operating system, which is a popular collection of framework for developing robot software. Using a ROS tool, we can see just a part of the full ROS environment that includes more sensor and device. It contains the main nodes and their connected topics. We have here the first node, that is the robot node, which is an interface between the KUKA cabinet, which is programmed in Java, and ROS, used for control the manipulator. We have also the natural control node, used to get the voice command from the user, and which is the target of this presentation. And also we have a main program, which is the link between the natural control and the robot. So this image describes in more detail the developed node. In the left side, we can see the ROS concept uses to integrate this node with the other part of the ROS environment. We have topics. In our case, this node works as a publisher, sending to any subscribed node the voice command recognizes by the implemented interface. And also we have services used for communication purposes, like select a specific interface or set up internal parameters. In the right side, we have defined two blocks or interfaces. The first is a direct connection with the TED queue via Ethernet, and also we have another interfaces that support the use of some online or offline tools for speech recognition. We can use with this node any of those blocks or interfaces to recognize and generate the control order from the user voice. So the TED queue, this is a standalone device capable to detect predefined word and sentences from a microphone. Using a REST API, this device sends through its network interface a number according to the voice detection. To accomplish with the objective of use the voice command to solve possible problems, we configure the TED queue to detect the following text. Note that that texts are not the traditional guiding command for control action of the manipulator, like up, down, left, right, or pick. No. In this case, this text can be grouped to handle two states. For example, stop any action of the robot and return to home pause. This will be useful when the operator prefers to perform the task by himself. And also we have the possibility, for example, to pause and restart the current action. For example, when the operator detects something wrong with a component involved in the task, then the operator can pause it, temporarily the robot, reposition the component, and resume the activity of the manipulator. Also, we created a simple and configurable graphical simulator for developing and testing purposes. This simulator helps us not to say the text, because could be tedious repeat the same multiple times during the development, and also allow us to use this interface without the TED queue. And in the other hand, we using the speech recognition. This is a Python library which supports several engines, and we keep it the ROS node with a flexible tool for recognize the speech from several languages. The operation of this library can be divided into three parts. The first is the read audio from a source that could be an audio file like MP3 file and or a microphone, for example. The second part is recognize what the user say using some online or offline tool like a Microsoft Azure, a Google Cloud, Houndify. And the second part is the output, the transcription as a raw text from the selected speech recognition engine. Our collaborative prototype is designed in a first instance to work with people which speak Spanish and or Basque. Also, even when some of these engines integrated by default with the Python library support Basque, we developed an interface for the Aditu live services. This last one is a dedicated services for speech recognition. And from a programming side, these interfaces receive the same object that the other engine and output the most likely translation using the same format. So now, using the configuration services, the ROS node can be set up for use the Aditu like any of the other interfaces. At that point, we have a ROS node with the capability of recognize and get the transcription from the speech. This could be enough for use the system just for guided manipulation, but not for problem solving, which is the main objective. Then it is necessary to include some implementation from natural language processing. This is why we developed these 4 options. The first option is use just the raw text. This option is very suitable for guided manipulation. However, it could be used for all purposes is really on the main control program. For example, classifying and defining execution tags for each command using conditional statement from programming. But this way can reduce the flexibility and scalability of the system because a small modification of any word or sentence needs to be reprogrammed in the main node and in other connected nodes. Why we implemented the second option, which allows us to make inside the natural control ROS node the classification and grouping of the transcription according to the semantic content, and output to the ROS environment use a keyword. This gives to the system the flexibility and scalability by concentrating on all possible changes just in one place, that is inside the ROS node. Also, the third option supports the use of classical symbolic methods for natural language processing. The classical symbolic methods are based on rules and they involve steps such as text segmentation, tokenization, identification of the part of speech, for example, noun, pronoun, verbs, and syntactic analysis and semantic and pragmatic analysis to understand the meaning of the text. We use the natural language toolkit, which is a Python library for symbolic and statistical natural language processing. Also, the fourth and last option is to use machine learning method for natural language processing. This method uses a trained agent capable of turning sentences into structured data. It can be used for identifying the user intention from a transcription. In our case, this option is not implemented yet, but it is on the table, and we want to use some of the platform presented like the Dialogflow or with.ai. So there is one important thing to take into account, and this is the ambient noise. The noise has a bad influence in the speech recognition. The engines typically recommend avoid the noise or background sound for increase the success rate. However, sometimes it is not possible to avoid the ambient noise. In our case, there are a lot of noise in the plant, but a preliminary test for the test cube gave off a rate over 88% of good recognition. Let's see this video recorded in the plant.
Vertical, origen, empujar, retraer, impedancia, grabar punto, arriba, escala 1, escala 10, delante, delante, abajo, detrás, derecha, izquierda, punto pivot, pivot A, pivot B, pivot C, pivot C.
So we have identified two ways to reduce or cancel the ambient noise. The first is use the speech recognition library, which has a function to dynamically adjust the energy threshold from a sample audio without speech. And the second one, we have in our plan to buy a dynamic microphone, like they use in aviation for helicopters, to try to reduce the noise. And with this video, I am going to end this presentation. This is a showcase of the developed prototype for pick the gasket from the door of a refrigerator. Let's see.
Empieza.
The order was start.
No sigas.
Don't continue.
Empieza. ¿Qué haces? Continúa.
This behavior is from a glitch from the video because it says continues.
Continúa.
The robot. This is the end. Thank you very much for your attention.